Often we have to make assumptions in friction. This means that we need to know if an object is behaving one way or another, because usually there are multiple ways for an object to behave. The two we will cover are slipping versus tipping and rolling versus sliding. It is always important to prove that whatever assumption you make is true or false. Often the best way to do this is to try all possible ways and show to the teacher through logic that your answer is correct. I'll show you an example of this. So here's the explanation of slipping versus tipping. In the case of an object such as this box, it can move one of two different ways. It can either tip over or it can slide to the side. In this example problem, we are going to be finding the minimum force required to make the box move, and how it will move, by slipping or by tipping. In both cases, the normal force is going to be equal to the weight of 40 pounds. But notice how there is going to be a difference in placement for the slipping and for the tipping. When the box is going to slip, we have no idea where that normal force is going to be at. But it won't be in the middle due to the applied force. Then if the box is tipping, it is going to be at the very edge of the box because that is the point that the box is going to pivot about. If something is going to slip to the side, that means that the force is going to have to overcome the friction on the bottom face of that box, which means that friction will have to be maxed out before it is overcome. That means we can use the equation that friction is equal to mu times n. However, if it's going to tip, that means that it didn't necessarily reach the max friction value until the applied force was too much that it began pivoting around the corner and tipping. In other words, we do not know what friction is equal to when it's tipping. Now you may become curious as to how you will solve this problem. Looking at the slip diagram, we notice that there are two unknowns, the placement at the normal force and what is the force. And then we look at the tipping, and we notice that we don't know what the friction force is and we don't know what the force is to make it move. That means that we need to solve for both these problems differently to try and find our answers. Since we don't know distances in slipping, we can't take moments. But since we don't know forces in tipping, we can't sum forces in the x direction. We can, however, do the vice versa for both. When we sum forces in the x direction on the slipping free body diagram, we immediately find the required force to make the box slip is 10 pounds. When we take a moment about the point where the normal force acts in the tipping free body diagram, we find that the force required to make the box tip will be 26.66 pounds. Now which answer is correct? If you said that the 10 pounds required to make the box slip, then you are correct. That is because you will push 10 pounds of force way before you ever reach the 26.66 pounds required to tip the box over. Good job. Now let's look at an example of rolling versus sliding. This one is more of a conceptual problem than it is a difficult problem. In this problem, we are going to separate the roller from the box and use two free body diagrams to decide which force P is needed to make the two objects move. In this kind of problem, our free body diagrams will look the same. You might be curious where, then, is the difference between the two assumptions. In both cases, the box will slide or overcome its frictional force. Take a moment to think about something rolling at point A. That means that the roller doesn't actually move at point A, but that the roller itself pivots over this point. Think of our tipping example before. That means that our frictional force was so great that in order for the roller to move at all, it must pivot. And since the roller is wanting to roll, the friction force at point C was resisting that rotation. And it must be overcome. When something must be overcome in friction, that means that it is equal to mu times n. That means that the friction force at point A, which is not overcome, is not equal to mu times n, but the friction force at C is. Now let's look at when the roller slides. In this case, the roller is able to overcome the friction at point A, so that instead of rolling, it just slides and moves to the right, almost like the box in this example. That means that the friction force at C was so great that it didn't allow the roller to rotate. Since the frictional force at A was overcome, that means that it is equal to mu times n, and that we do not know what the friction force at point C is. Now we can go ahead and set up our equations for equilibrium that are applicable to both free body diagrams. First, since we know that it is sliding at the box, we can assume that friction at the box is equal to the normal force times its static coefficient, mu. Then we sum forces about our box. Then we sum forces around our roller. Now we need another equation, and since we don't have an actual length, this might seem really hard. If you were able to take a moment about the center of the roller, however, you would notice that almost all the forces cancel out except the frictional forces. And since the forces are equidistant apart, the radius, you can basically neglect the distance. Now that we have all our mutual equations, we can look at the real difference between the two free body diagrams. As I said, for when the roller decides to roll, it has overcome the friction at point C. This means that our friction force at point C has to be equal to the friction coefficient at point C. Next, if the box were to slide at point A, then it would have to overcome that friction force, which means that it is equal to the friction coefficient of A times its normal force. Now we can simultaneously solve all these equations using either of the conditional equations, and we get these numbers. First, for when it rolls, second for when it slides. Now the important part is to look at the force P to determine which is the actual answer. We notice that P is less when the roller rolls. Therefore, these objects will move when P is just greater than 11.67 pounds.